Okay, let's get started. Okay, so here's some reminders about the master exam. When you take the master exam tonight, very important reminders. The first is, the first half of the test is 25 short ones. You're going to do all 25. Do all 25 short derivatives. And then the second half is where you're going to be, there's going to be a system that's going to tell you, you do these 10. Okay, so only do the 10, do exactly the 10 that you're assigned, okay? And that's the whole test. And the 10 are from the list, from the bank that I gave you, okay? So whenever an expression is presented as a quotient, you must use the quotient rule. So it is possible to make it into a product and use the product rule, but you need to show proficiency at the quotient rule. So whenever the function is given as a quotient, you need to use the quotient rule, okay? So in the past, students have written things that when you read it, it's implying that the function is equal to the rate of change function. If you do that, that's really terrible form. You will get a 0 on the problem. Do not ever write anything, any expression that says that the original function is equal to the derivative. Those are two different functions, and we've worked hard on that, right? The rate of change function is not the same as the accumulation or the amount function. They're different. So don't write that they are. Okay? And then last thing is a very common mistake students make is they multiply, you end up in lots of these chain rule problems, you multiply by a sum or difference. Okay, you multiply by a sum or difference. If you don't put parentheses around those, then mathematically that's incorrect. So just like, for instance, we did the one the other day. It was something like square root of sine x plus x to the 1.5 or something like that. That was the fault width. That was the fault width after x seconds went by, or x months, I think, x months. And so you're going to do 1 over 2 square root of the interior as it is. And then so this is what students sometimes do. Say times cosine x. Now the derivative of the interior, cosine x plus 1.5 x to the 0.5. This is a very common thing that students do. Multiplying by a sum or difference and not using the parentheses. So why is that incorrect? Why is that not right? You see that it's not right. If you put that expression in GC to check to see if your rate of change function is right, it will not graph the right rate of change function. Why not? Yeah. Right. Right. What is this going to do? So this initial fraction is going to get multiplied by what? Only cosine x, and then it's going to add 1.5 of that to the whole thing. And that's not what you want, right? You want this fraction to be multiplied by the rate of change of the interior, the whole thing. So this is different now. That's different. So whenever you're multiplying, you're chaining on, you're multiplying by a sum or difference of things. You need parentheses around that. So you're multiplying by that whole sum or difference. And that's important. So that's a very common mistake students make also. Okay, questions about the mastery exam. So you're showing up tonight between 6:15 and 7:30, same place, basement of PSA or Wexler, room 21. This will be shorter though, so getting through the mastery should be shorter than an hour exam. Yeah. One problem. Well, is it? Yeah. Okay. We'll do one. Sure. What is it?
It's just a piece of the problem. So it's log base 4 of 5x.
Okay, so here the same question. So log base 4 of 5x, like this. So the rate of change of that right there. Okay. So what's the structure of this? What's the structure of this? Log, right? So it's chain rule, and the exterior function is log. So what is the rate of change of log? Yeah?
Oh, sorry. 5x.
Okay.
4
Times?
times
Right. Done?
and then the chain rule is 5x.
Times 5x. Times what?
5.
That's 5. So what was your question?
I was just when I was looking at the rules of general, I thought it would be 1 over 5x element 1. I wasn't sure if you would have to take the chain rule of that.
Yeah, whenever, in any composite function, if you have one function plugged into another, in any situation like that, it's got to be the chain rule. Derivative of the exterior with respect to the interior times the derivative of the interior. Yes?
If we don't put like multiplication sign in the middle, would we get points deducted for that?
No, that's fine. Yeah.
So since this one doesn't have a minus sign, it's from 5.
No. So it's only when you're distributing, right? You want to multiply something by a sum or difference of terms. If it's just a single term, then there's no need for parentheses. Yeah. ln of what? Natural log of 4x would be 1 over 4x times the derivative of 4x times 4. How'd I do? How'd I do? 0 on the mastery for that. 0. Why? No? No? Yeah, what did I just say? I mean, what did I just say by writing that? What did I just say by writing that? I just said that the original function, what? It's a big deal. These are not equal functions. These are not equal functions. Students do this all the time. But they're not. That's what? Amount or accumulation? That's the rate of change. They're not equal. So that would be 0. So what do you do instead? So bare minimum, you could put an arrow, or you could, define, say y equals log base 4 5x, and then dy dx or y prime equals yada yada yada. So that's good form. That's good form. Okay. But that does not equal that. So if on your exam, if you write something like that, 0 on the problem. Yeah. Yeah, so if you did on the left side, if you wrote dx, now they're equal because it's the rate of change of that function. That's right. So now we can put equal. Yes, that would be fine. That's perfectly fine. Okay, last chance. Questions about the mastery? Yeah? After class. We've got to move on. Just general, not specific derivatives, but general administrative details. Okay, we'll see you tonight. It's about that. Okay, so this weekend will be the first installment of an online homework system called WebWork. Okay, we're going to start using WebWork. Okay? And so I'm going to put an announcement. Can I have your attention, please? There'll be an announcement on Blackboard that'll explain all the things you need to know to get started on the system. But it's kind of like just jump in and start working with it and kind of learn as you go. But I will have an announcement that has the full instructions of the things you need to know to do it. And so that will be, and then the WebWork assignments will always be due a half an hour before class starts. So that one will be due Tuesday at 1 p.m. Tuesday at 1 is the deadline for credit for that. Okay? So Blackboard will have all the information you need to get you to the right place and to use that system. Okay? And we have not abandoned Top Hat by any means. We'll still have some Top Hat here in the days ahead. Okay, so we left off with looking at, we put together a sketch of an amount or an accumulation function based on looking at values of the rate of change, right? We were looking at values of the rate of change. Remember this? in intervals. And based on what the rate of change was, we kind of put together and deduced what the amount function was like. Okay, what the amount function was like, and we came up with that red. So you see this red curve here. That's what we came up with on Tuesday. So let's just. And so the black bar on the x-axis is showing the current value of x, also shown by the point on the graph. And then the red graph is our amount or accumulation function. And then the blue line is a way of showing the rate of change. I think we started at. Okay, so that blue line is a way of showing the rate of change, because we think about how did we find rate of change? How have we found it all semester? How have we estimated it all semester? What did we do? So here I am at negative 1.11, and we say we want to estimate the rate of change at negative 1.11. What did we do? We've done it several times throughout the semester. I want to know the rate of change of the red accumulation graph at this particular value. Where is Adam? What do we do, Adam?
You do there, take 2 fourths or
Yep.
yeah, fourth, 1/4, 1, and 1 close to it,
Uh-huh.
and then do dy dx. Get the rate of change.
Well said. So we would zoom in until the graph appears linear, right? And so we say if the graph, we can zoom in and we can get that graph to look straight, then we say we have rate of change at that moment. And then we take 2 points, do dy over dx. And so let's just zoom in here. And so that blue line, look at that blue line. Okay, so I'm going to zoom in on the red curve. And what happens eventually? I'm zooming in. Right, so this is the idea of that rate of change of the moment. So that blue line is, when we zoom out, it's a visual of this idea that when that we have a rate of change at the moment, that when we're zoomed way in, it's essentially linear. Okay? So as x changes, that blue line is a visual of the current rate of change. All right, so now in this interval from -3 to 2, where is the accumulation decreasing? So where's the accumulation function decreasing? How do you know? And there's 2 separate ways that you could justify that f of x is decreasing. So I want you to talk about that. Where's the accumulation decreasing from -3 to 2? And 2 possible ways you could justify your answer. Go, talk. Okay, where's Rashed? Alamani, Rashid. Rashid, did you drop? Estrelita, Naswood. Where's Estrelita? Luis F. Figura. All right, so did you come up with where for what values of x is f decreasing?
This is decreasing at 1.5 all the way to 1.2.
Okay, so he's saying from about 1.5, maybe a little bit over here, maybe like 1.8 maybe, to about 1.2. Agree with that? About negative 1.8 to about 1.2. And so what was one possible way that you could say, this is why it's decreasing on that interval?
You could see the f of x is going down.
Right, yeah, so that the graph is going down. It's going down, it's decreasing. Y values are getting less as x increases, so the graph is going down. Okay, how about the other way that we could see that f of x is decreasing? Hector. Is Hector here? How about Dongfi Zhang? Dongfi Zhang. What's the other way that we could see that the accumulation is decreasing besides just that the graph is going down? The rate of change is negative. Got it. So when the graph is heading down, the rate of change is negative. So that's where that blue line has a negative slope, right? That blue line has a negative slope. It's pointing down. And so starting right now, we look at R. It's negative. It's negative. It's negative. It's negative. Negative, negative, still negative until when? Until right about now it turns positive. Good. So and then I want to make sure that we have our So what did we say? We said that when a function's values are increasing, the rate of change is positive. And so this is the case we just looked at. When the function's values are decreasing, you can tell that by seeing that the rate of change is negative. Okay, so what's going to happen here is I'm going to ask you a series of questions, take you through an activity, and everything's going to be going smoothly. And then in a very short period of time, it can get very confusing very fast. And I'm doing everything I can to avoid that, but it's just the nature of it, okay? Whenever that happens, we go back to these facts. If you can go back to these facts, if any kind of function is increasing, the rate of change of that function is positive. And when any kind of function is decreasing, the rate of change is negative. So it's that's our bedrock, okay? It's our reference point that when it gets confusing, if we go back to that, we can usually get unstuck. Okay, so we're gonna keep that. How do I get rid of that? There we go. So we're going to keep that on the top of the screen there and hold that right in the forefront of everything we're doing. Okay. So now, second question, where's the rate of change in this over this course of something like negative 2.5 to 2 or 2.5? Where's the rate of change decreasing? And so remember, there's two ways that a quantity can decrease. And this is going to be important. How can something decrease? It could be getting less positive, or it could be getting more negative. That's when something's decreasing, it's one of those two. It's getting less positive, the values are getting less positive, or getting more negative. So now I want you to talk about that. So where in this interval is the rate of change decreasing? Where's the rate of change decreasing? Talk. Go. Okay, so this is a little not quite as easy. So, David, where did you guys say that the rate of change is decreasing? For what x values?
From negative 2.5 all the way up until positive like 1.3.
Okay, so starting here from negative 2.5 all the way until negative 0.3. So like there? All right, so he's saying, so basically all the way starting from the left, all the way until about here. And why do you say that? Can you say why do you say that?
Actually, it was from like where you have the hash mark, actually decreasing up to 0.3, but not all the way from the left.
Oh, okay, so now you want to start here. So the rate of change starts to decrease here until when?
Until negative 0.3.
From there to your conjectures, you're saying from here to here. All right, so let's talk about this section right here that you just cut this out, right? So what is the rate of change doing there? Is the rate of change positive or negative? Less than whatever, negative 1.8. Is the rate of change positive or negative? Is it becoming more or less positive? So rate of change is decreasing or increasing? Okay, so it is decreasing here because the rate of change is less positive. And then what about this next section? The rate of change is positive or negative? Getting more or less negative? So positive increasing or decreasing rate of change? So you guys are telling me as a class that it's decreasing all the way through here. I heard, yeah, no. Somewhere around here. Okay. Do we all agree with that? Okay, talk to me. Who said that? Yeah, what's going on?
The rate of change is kind of at like negative 2.5.
Okay.
It starts to decrease, and then it stops decreasing right around the red line.
Right.
The first one, but then it starts to increase again
Okay.
until you get like then it goes constant, and so then like right here it starts to decrease again until the end of the red line.
Okay.
You get to, like,
So the issue is when the rate is negative, what does decreasing and increasing mean for negative rate? So Shoot, I can't stop this. Okay. All right. So right here, in this section right here, is the rate of change positive or negative? Negative. Okay, and so then if we increase x a little bit, did it just get more negative or less negative? More negative. So values that get more negative, are those increasing or decreasing? In or D? If it gets more negative. Decreasing. So yeah, it's bigger negative. So they're bigger negative, but larger negative values, if I wrote a sequence of values like this. Where am I? If I wrote this, -5, -10, -20, -50, -100, is that list of numbers is decreasing or increasing? Is that a decreasing list of numbers or increasing? Do you see it's decreasing? And that's what's happening to the rate of change. The same thing as something like that. The values are getting more negative. Okay? On a number line, we're moving left on a number line. In positive territory, getting less positive. If we keep moving left, getting more negative. Decreasing all the way. Okay? So I mean, I'm glad that you spoke up and we're having this conversation, because that's what's tricky. That's what's tricky. You want to see this as, because the numbers, the values themselves, the magnitudes are getting bigger, you want to think of that as increasing. But in order for us to be consistent with positive and negative, we have to see that as a decreasing list of numbers. And so then through this part of the graph, the rate of change, as it gets more negative, the rate of change is decreasing through there. So now, is the rate of change getting more or less positive or negative here? More or less positive or negative? Through here. Less negative. Less negative. There's negative rates of change, getting less negative. So are those rates increasing or decreasing? In or D? Increasing. And then the rates are getting more positive. So starting here, all through here, the rate is increasing. Getting less negative or more positive. So ask me. Who has a question? John, do you have a question? Someone next to you have a question? Okay. I heard a question. But ask me. Let's talk about it, because other people are probably thinking the same thing. Okay. Going on. Yeah, question, yeah. From what to what? 3 is off the screen. Negative 2.8. Because is the rate of change positive or negative over here? The rate is positive. Is it getting more positive or less positive? Less positive. When values get less positive, decreasing, right? Decreasing. Other questions? Okay, new question. So when R is decreasing, that's over here on the left side, right? I've marked that off in blue from here to here. It's decreasing. What can you say about the rate of change of R? Well, we know that. We've already talked about that. So just go right to B. What can we say about the graph of F? Look at where R is decreasing. That's from here to here. What can you conclude about the graph of F? Is it decreasing? If the rate of change is decreasing, is F necessarily decreasing? No, because it's increasing here and then decreasing. But what is true about F for that whole interval where R is decreasing? Yeah. Okay, but so what can we conclude about F? So the red graph is the accumulation function. What can we conclude about F wherever R is decreasing? What's that? This whole thing could be down here. The whole graph could be down here and nothing would be different, right? The whole thing could be shifted down. So it's not that just that f is positive. Yeah,
It's not like a downward or kind of thing.
right. Exactly. So when the rate is becoming less positive or more negative, what? The graph is like turning clockwise. Do you see that? It's turning clockwise. Regardless of whether it's increasing or decreasing, the accumulation is turning clockwise for increasing x. So watch the blue line. Ready? I'm trying here. Okay. So watch. Ready? Turning clockwise. So where r is decreasing, f. Oh. That's not my name. There we go. F is, for f turns clockwise. Wherever r is decreasing. Right, it's because the rate is decreasing. It's like you think the accumulation it's like slowing down. So it's turning, it's bending downward like this. Okay, and so then we also call that's also called concave down. And so concave down is like a what? Concave down. Like a frown. Right? So a helpful way to remember it. Okay? Concave down. So cup downward is like a frown. That's where the function's turning clockwise for increasing x. Okay, then over here we said r is. So here the rate is getting what? More or less positive or negative through here? The rate is getting more or less positive or negative? What is the rate positive here? People are saying positive. The rate is negative. More or less negative? Less negative. And then more or less positive or negative? More positive. The rate's getting more positive. So through this whole thing over here, r is increasing. And then what can we say about the graph of f? Okay, before that, it's turning. Do you see that it's turning? Let me show you. You see that it's turning counterclockwise. Look. Watch. Turning counterclockwise around like this. Accumulation, it's increasing. Accumulation, the rate of accumulation is increasing. So it's bending up, right? It's bending up. Less negative, more positive, the rate. So F turns counterclockwise. And we have concave up. Okay, like A. It's got to rhyme with up, though. Cut. Okay, I'm willing to endure your Snickers if you learn it. If you learn something, okay? All right, so what we're talking about is what can we say about the accumulation when we're qualifying the rate as increasing or decreasing? So we already know that how we can qualify the function if we know if the rate is positive or negative, right? So that's our original stuff up there. If the rate is positive, the function has to be increasing. If the rate is negative, the function has to be decreasing. But what if the rate is decreasing? Then what can we say about the function? The rate itself is decreasing. Well, it could be getting less positive or more negative. That's a decreasing rate, and we know our function turns clockwise in that case. Or it's concave down. And then if the rate is increasing, the original function turns counterclockwise, or it's concave up. Okay, so now it's getting a little more complicated, right? So a lot more stuff to keep track of. But again, going back to our original two things are kind of our reference point. All right, so let's see. So now let's ask this question. Over here where the rate is decreasing, what can we say about the rate of change of R? So R is its own function. It has a rate of change. So if that rate function R is decreasing, what can we say about the rate of change of R?
Negative.
What's that?
Negative.
Why?
Because the rate of change is decreasing.
Okay? So when any function is decreasing, what about its rate of change? It's negative, right? If a function's values are decreasing, it doesn't matter what kind of function it is. Its rate of change is negative. So now we're talking about the function R. The function R is decreasing. Then its rate of change, the rate of change of R, the rate of change of the rate, is negative. So the rate of change of R here is negative, and then starting here, the rate of change of R is positive over here. So now we're going to start talking about the rate function for R, or the rate of change of the rate of change. Let's talk about that. Any questions on this so far? Okay, so look, I've got some function graphed here, or some function that's defined in GC. R1 is the rate of change of that function. Okay? R2 is the rate of change of R1. That's what we just started talking about, the rate of change of the rate. So now look, I'm going to show you here that at n equals negative 2.4, that's where we are right here, negative 2.4. R2, the rate of change of R1, is negative 4.32. So based on that value of R2, what can you conclude about R1? And then what can you conclude about F? So this is, can you put stuff together here that we've talked about? So now you have R2. What can you conclude about R1? And what can you conclude about F? Go, talk this out. All right, where's Jesus? McQuarrie. Jesus McQuarrie. How about Ella? Alcantar. Ella. Okay, how about Yuyi Wang? How about Michael Alvarado? Michael. So what'd you say? So we got R2 is negative. It's negative 4.32. What can you conclude about R1? What's that? It's also negative. What do you think? Agree? If R2 is negative, that means R1 is negative. So R2 is a rate of change function. When a rate of change function is negative, what does it mean for the function from which it came? Back to that. If the rate of change is negative, then the function is decreasing. Well, R1 is the function for the rate of change function R2. So you should have said, when you talked, R1 is decreasing. So if R2 is negative, that means the rate of change of our function is decreasing. And what's the conclusion? If R1 is decreasing, then R1 is getting either what? If it's decreasing, where's 1? Moreno.
Getting more, less positive and more negative.
Less positive, good. Less positive or more negative. All right, so if the rate of change, if R1 is decreasing, that means it's getting less positive or more negative. And what can we conclude about F? We just talked about this. So the rate of change decreasing. So what is F like from the fact that R2 is negative and R1 is decreasing? What is F like? Yeah, John?
Heading clockwise.
It's turning clockwise. Turning clockwise. Or concave down. All right, so all we know, so the only thing we know from the fact that this is negative here is that, so it could be like this. Do we know if F is increasing or decreasing? No, right? We don't know. So it could be like that, or it could be what? It could be like this. At that value, as long as it's turning, all we know about F is that it's turning clockwise. It's turning clockwise. So now I'm going to give you some more information. I'm going to give you R1, the current value of R1. All right, so now I just gave you R1 at the same X value. So go through the questions again and see what you can, what more conclusions can you make? How can you be more specific now that I've given you R1 and R2? Go. Okay, where's Andrea Lopez? How'd it go? Did that help? Seeing R1? So what about, so is R1 still decreasing? Is R1 still decreasing? Okay. Is it getting less positive or more negative? Right, well, now we know R1 is positive, so it must be getting less positive instead of, it can't be getting more negative anymore. So it must be getting less positive. And then what can you conclude about F? It's what? Okay, it's concave, so concave down, but with it, we knew that before, right? But what more do we know about F? So now we know that R1 is positive. So then what do we know about F? What's that? What's that? Increasing. So now we know that because R2 is negative, it's concave down or turning clockwise, and now R1 is positive, so F is increasing, right? And if we put that together, we know now kind of in the vicinity of x equals negative 2.4 what the graph looks like. So can you draw it with your finger now? Draw it with your finger. At around 2.4, what does it look like? Yeah, increasing but concave down. Increasing but concave down. So concave down meaning the rate is decreasing. So the function's increasing because the rate R1 is positive. But it's concave down because rate 2 is negative, which means rate 1 is decreasing. Did you catch all that? So you gotta keep track. And again, it's all going back to these two statements. But when we say the function's values, that could be f or that could be rate 1. That could be rate 1, and so then it applies no matter which function you're talking about. All right, so I'm going to give you a new scenario over here. So here's x equals 3.5. So now we're over here in positive territory. So where were we? It was that negative 2.4. So for negative 2.4, we concluded that just in that vicinity, it looks something like this at negative 2.4. Okay, so now here we are at x equals 3.5. You've got R1, you've got R2. We should go through the questions again and analyze the situation. Go. All right, where's Braden Silcott? Braden, how'd it go? The whole thing. So, based on the values of R1 and R2, what can you conclude about R1? What can you conclude about rate 1 based on the values you have? Why and why? But R2 is negative. Since R2 is negative, R1 is decreasing. Anything else you know about R1? Okay, that's true. So R1 is decreasing. We know that because R2 is negative. But I also gave you R1. So what else can we combine with the fact that R1 is decreasing? It's also... So, yeah, so it has to be, it's negative. So therefore it's getting more negative. So I could also highlight this. So we know, because we have R1, we know it's also negative. So it's negative because I showed you it was negative, but then it's decreasing. We know it's decreasing because R2 is negative, and so therefore it has to be getting more negative. Decreasing rates getting more negative. Okay, so now what two things can we conclude about F? Where's Brenda Esparza? Yeah, so what two things can we conclude about F now? So we can conclude that F is negative? So let's just do it one thing at a time. So from the fact that R1 is negative, what can we conclude about F if R1 is negative? Decreasing. This tells us that F is decreasing. And what does R2 being negative tell us? Any volunteer? Anybody? John? Okay, so and then what does that tell us about F? The rate, so R1 is decreasing, that's right. Therefore, F is concave down or turning clockwise. Concave down. So around 3.5, draw the graph with your finger. Around 3.5, draw the graph with your finger. Decreasing, concave down. Decreasing, concave down. Something like that. Okay, so I'll turn on the graph, see if we agree with what we got. So we looked at only 2x values, right? We only looked at, so we only know about 2x values. Negative 2.4 right here. And 3.5, which is right about there. And so at negative 2.4, what R2 was negative, and R1 was positive. That means F is increasing, but the rate is decreasing, so it's concave down. And then 3.5, we saw both R1 and R2 were negative, meaning that F is decreasing, and the rate is decreasing, getting more negative. The rate's getting more negative. Okay, so you'll have lots of practice with this in the homework, but you just need to practice. It's the kind of thing where it's like you're getting it for a while, then all of a sudden you come to a problem and it's like you don't get anything at all. This is natural. And it's like you got to reconstruct it all over again. You got to start over. That's why we'll give you as many practice problems as you can. But it's just you have to kind of go through this deconstruction and reconstruction phase several times until it finally starts to stick. It's just the nature of this. It's hard, okay? But let's summarize. So what we started to talk about here? We started talking about the rate of change of the rate of change. The rate of change is the rate of change. So here would be one way to express that. dr sub f x dx. So this is the derivative of the rate of change of x. Or the derivative of the derivative. Or the rate of change of the rate of change. Okay? So the derivative of the derivative is called the second derivative, right? So now all these mastery problems that you're doing, we just call them the derivative. So to be more specific, we could say those are the first derivative. Those are all those problems you're going to do tonight on your exam. Those are finding the first derivative of a function, which is the rate of change of that function. So now the derivative of the derivative is called the second derivative. So here's other notations for the second derivative. Okay, so these all mean take the derivative of the derivative. So d squared f over dx squared, d squared y over dx squared, f double prime or y double prime. And we found out the second derivative is telling us about how the first derivative is changing. So it tells us how the rate is changing, whether the rate is increasing or decreasing. That's what the second derivative tells us. If the rate is increasing or decreasing, and if the rate is decreasing, then our original function is turning downward, or turning clockwise. And if the original function, or if the rate is increasing, then our original function is turning up. The rate is increasing, it's turning up this way. Okay, so let's kind of put it all together here. So the function's output y is increasing. What does it mean for the rate of change? Positive. Okay, well, so we've said that many times. Now let's do a mini proof of that. Let's justify this. So justify this equivalence, given that the function is increasing. So this is our given over here. Given this, prove this. And here's your hint. The rate is calculated by dy over dx. So given that y is increasing, how can you prove that k is positive? So work on that. So given the fact that y is increasing and k equals dy dx, prove that k is positive. So it's like a three or four step proof by deduction starting with the fact that y is increasing and that k is dy dx, prove that k is positive. Can you do it? Take a couple minutes, see if you can do this mini proof.
Okay, but let's read it. The key to this group is considering final y and initial y. That's what you got to think in terms of final y and initial y. That's kind of the length from your given to what you're proving. Okay, keep talking.
Okay, volunteer to talk me through you think you could talk me through a good deductive proof here? Given y is increasing, proving that k is positive. I know lots of you got the right idea, so yeah, go ahead.
Okay, y increasing is always going to be at a top.
Okay.
So if you're increasing in x, then that means the change of y will be increasing. So you have a positive over a positive, which will equal a positive rate. If you're going decreasing in x, the y is going to be negative or less, so you're going to have negative over negative, which will still equal a positive.
Okay. Yeah, so do you guess what he said? The first half of what he said is the most important part. That if y is increasing, then how does final y compare to initial y? Bigger, right? Final y has to be bigger than initial y. And so then your change in y, dy, is greater than 0. And if dy is greater than 0, then k is greater than 0. So that's the idea of a proof, right? So every conclusion you make is rock solid. You know it for a fact based on what you said before. And then you make its chain of these conclusions to come to your final conclusion. Okay, does it make sense? All right. If the function's output is decreasing, then what is the rate of change? Negative. 1 minute. Prove it. 1 minute. Go. Prove it in 1 minute. Okay, Brandon, Zavala. Brandon here? Did you get it? Did you get started? So if y is decreasing, then what about y final versus y initial? How would y final compare to y initial if y is decreasing? How does y final compare to y initial? Not sure? Okay, how about Ada? Y final is less than y initial, so then what? And therefore? That's it, right? So if y is decreasing, your final y is less than your initial y. Which means that the change in y is less than 0. And that means that k is less than 0. So this is all assuming assuming a positive change in x, right? Assuming a positive change in x, final y less than initial y, if y is decreasing. Gives us a negative dy and a negative rate. Okay, so that's proving this. Again, it's going back to it goes back to this. Values of the derivative are positive, values of the function increasing. Values of the derivative negative, values of the function decreasing. Okay, so, and then we've said before, these basic principles hold true for any function and its derivative. F prime and f. But the same principle holds true for the second derivative with respect to the first derivative. Right? If the first derivative is decreasing, then the second derivative is? If the first derivative is decreasing, then the second derivative is negative. If the second derivative is positive, then values of the first derivative are increasing. Okay? So then there's just one additional idea that we've already talked about, kind of completes the whole picture here. And that is, what does f, so if the second derivative is positive, we know the first derivative increases, and we showed earlier that the function turns counterclockwise. Right? The rate is increasing. It's getting less negative and more positive. It's speeding up. The accumulation is speeding up. So it's slowing down, getting negative, or speeding up, getting positive. So the rate, the function turns counterclockwise. And then if you have that the second derivative is negative, and we know the first derivative decreases, then the function is turning clockwise, right? Bending down. The accumulation is slowing down or speeding up negative, right? Because the rate is decreasing. Okay, any questions on that? Okay, so optimization. So this leads us to what, these principles lead us to talking about what's called optimization. So first of all, critical values. A critical value of a function f is any value of x where, first of all, the value of the function exists, so you get a valid output. And here's the critical part, that the first derivative is 0 or the first derivative does not exist. So the function value exists, you plug in a value, or you plug in this x value, you get a value of amount or accumulation. But the first derivative is 0 or the first derivative does not exist. That's what defines what we call a critical value. Okay, so in this case here, c is a critical value, right? Because the value of c is making the first derivative equal to 0. Okay, so c, as long as c gives a valid output of f, then the c is a critical value of the function f. And so what does it mean for the first derivative to be 0? So how would you talk about what's happening with the function if the first derivative is 0? Let's see. Miriam Alawarty. Where's Miriam? Miriam Alawarty. Samuel Rochnick. Samuel. So
maximum or a minimum?
Maybe, but let's see. Literally, what does it mean? So that's kind of a conclusion we can make, maybe. But what literally does it mean if the first derivative is 0?
It's switching from positive to negative or negative to positive.
Okay. All right. What's that? Yeah. So yeah, Farrah said. So the function itself is not changing, right? So like at least for one moment at c, it's not accumulating any positive or negative values to the amount. So if that's true, then f stops or pauses momentarily, increasing or decreasing at c. It's not increasing or decreasing. The rate is 0, so there's no increase or decrease. And if it's a critical point, then it's just for that one moment. It's just for that one moment. So we're going to investigate the different situations you can have for the first derivative equaling 0. Or the different situations you can have for the first derivative equals 0. So this is what Samuel said. He said a local max. So if you look at that graph right there, here's what it looks like dynamically. So really, talking about a local max for this critical point is not just about focusing on C, but kind of in the vicinity of C, or in the neighborhood around C, what's happening. So there's really 3 things that are happening in the context of this local maximum. So I want you to keep your eyes on, first of all, watch the black arrow. Watch the black arrow. What does the black arrow do? Yeah, increases constantly. And so this gives us a reference to look at what the y value is doing. So x is just very boring, just increasing constantly. So as it does that, now focus on the pink arrow, which is the dependent variable. And there's 3 things that happen that characterize a local max. There's 3 things that happen to the value of y that characterize a local max. So see if you can watch. So you're watching the pink arrow. Talk with the person next to you. What are the 3 things altogether that characterize a local max? Go. You're focusing on the pink arrow. Okay, where's Christopher Heston? Christopher Heston. Oh. So did you identify kind of the 3 things that happen that characterize a local max?
Constantly goes up, stop, momentarily pause, and constantly goes down.
Yeah, so he's saying so the y value goes up, it increases to the left for values less than c, right? And then at c,
Pauses.
there's a pause, right? There's a pause at the critical value, and then after for values of x greater than c, goes down, decreases. So this is the whole picture of a local maximum. Increase, and then pause at the critical value, and then decrease. That's what characterizes a local max. Okay? So look. If f is increasing, what does that tell us about the rate? If f is increasing, what do we know about the rate? Positive. At the pause, what do we know about the rate? And if f is decreasing, what do we know about the rate? So can you make just a general sketch, or in your mind imagine, or sketch in your notes, what will the rate function look like around a local max? You said that f is going up, the rate is positive. At the pause, the rate is 0, and the decrease, the rate is negative. Yeah, so tell me. Yeah. Right. Right, so over here it's positive, and then at C it must be 0, and then negative. So I'm making it squiggly because it's like who knows it's exactly what's happening. But the main thing is that when f is increasing, the rate's positive. It's up above, and then at C it's 0. And then it's still too squiggly though. Jeez. Butterfingers. Okay, something like that. Okay, so then what about, based on that rate function, can you sketch the second derivative? So what's the rate function doing? Can you sketch the second derivative? Last thing, go. What will the rate function, the second derivative, or the rate of the rate, right? The second derivative of the rate or the rate. Okay, Ian, you're up. So what is the rate doing, and how can then we make a sketch of the second derivative? Okay. Well, no. So it could be wavy. It could be a little bit curved. But in general, what is the rate doing? Decreasing, which means the second derivative is negative. So something like this. It's going to stay. If the rate is decreasing, then that second derivative is negative. So it's going to live underneath the x-axis. Did you have an announcement, or are you just telling us? Okay, yeah. All right. Anybody have a question? All right. 6:15 to 7:30. See you tonight.